Welcome to this presentation, an introduction to programmable logic controllers. This lecture will start at a very basic level. It does not assume that you have any prior knowledge of programmable logic controllers. However, there are some sections of this presentation that do require a fundamental understanding of basic electricity and magnetism. If your background is in computer science, this presentation will quickly enter into territory that you are already familiar with. After all, PLCs are computers and logic is, well, logic. I have attempted to make this presentation as generic as possible. However, the examples are based on a specific family of processors. Programmable logic controllers are the major component in industrial control systems. They replaced something called electromagnetic relays. The language used to program programmable controllers still uses symbology from the evolution from these relays to using computers to control manufacturing systems. So this section we are titling Relays to Bits, basically making the transition from using relays to using bits in memory. A brief bit of history is needed to build a background for some of the terminology and symbols used in programming programmable logic controllers. What you see here is a photo of one of the original relays invented by Edward Davy in the 1800s for the telegraph system. Without going into a lot of detailed explanations regarding the line losses of signal over long runs of telegraph wire, it is sufficient to say that to prevent the loss of the telegraph signal over these great distances, they installed relay stations to restore the signal level. So the original relay, and that's why it's called a relay, was a device for relaying the contact closure of a telegraph key at intervals along the telegraph wire as it traveled across the country from one end to the other. Once the relay became known as a device, it was not long before engineers realized that there were other applications for contact relays. If you could use a relay to relay a contact closure into an isolated circuit to restore the voltage levels, then you could use a relay to relay a contact closure into a circuit with an entirely different voltage type and level. In other words, using a switch that supplies 24 volts DC to the coil, but have the contacts that are switched by the relay actually switching a higher voltage, such as 480 volts AC, and switching heavy contacts to handle much higher currents. Enter the modern relay, which you see in the photo before you. The most dominant feature of a contact relay is the coil. The coil is also the load in the switching circuit. So the contact closure being relayed is controlling the coil, which controls the contact of the relay. The coil is wound around a pole piece, a rod of ferromagnetic material. And you know from your studies in basic electricity and magnetism that as current flows through the conductors of that coil, the electrons, which each are each a little magnet in principle. Each electron has a north and a south pole. When they're all flowing in the same direction, all the free electrons in the copper atoms, all of their magnetic fields join together, and inside of the coil you have a very intense magnetic field. Magnetic fields don't pass through air very easily. Air has a high resistance to a magnetic field. So if you place a ferromagnetic material inside of that coil could also be called a solenoid. If you place a rod inside of that coil of ferromagnetic material, that greatly intensifies the magnetic field. The object of the electromagnet's affection is the armature. The armature is another piece of ferromagnetic material that is suspended near one end of the coil by a spring that would oppose the magnetic field. Now keep in mind, remember we said that air is not a good path for magnetic field. Ferromagnetic material is. Another thing to remember is that the magnetic field is always trying to shorten itself. So when it sees that armature, that piece of ferromagnetic material, it is in the magnetic field, and since the field is trying to reduce its size, it pulls that ferromagnetic material hard against the end of that pole piece on that coil. Attached to the armature, as you see, the armature is suspended on a spring, and on the opposite side of the armature from the spring you have a moving contact. The moving contact travels are restricted in each direction by stationary contacts. When current flows through the coil, the armature is drawn to the pole piece of the coil against the tension of the spring. As the armature travels towards the coil, the moving contact travels as well. When the circuit containing the coil is opened, that is, turned off, the magnetic field collapses and the spring tension is now the dominant force, and the armature and the moving contact moves away from the pole piece. The movement away from the coil is limited by a stationary contact, and the movement towards the coil is limited by stationary contact. So, as power is alternately applied to the coil, the moving contact makes contact with the two stationary contacts. One contact when the relay is de-energized, and the other when the coil is energized. Let's look at this contact relay in a slightly different graphical manner. We have a diagram in front of you, and in the diagram you see a coil of conductor and two connectors to apply it in a circuit. You see it's wrapped around a pole piece. At the end of the pole piece you see an armature, another piece of ferromagnetic material, and it is attached on a lever that is spring-loaded to pull it in the upward direction. The lever with the moving contacts, that terminal would be called the common because it's common to both normally open and normally closed. The stationary contacts are called normally closed contacts, normally open contacts. The normal state for the relay is de-energized. When the coil is de-energized, the moving contacts are under the influence of the spring and held tightly against the normally closed contacts. So you have a complete circuit from the common to the normally closed contact when the coil is de-energized. When you energize the relay, in other words, you run electrical current through the coil, it produces a magnetic field inside the coil, intensified through the pole piece, passes through the armature, pulls the armature down against the spring, completing the circuit from the common to the normally open contacts, as shown here in this animation. I also added a little flex in the contact to show that the contacts are designed to have a slight wiping action when they make and break contact. That's to clean off any carbon caused by an arc, and it leaves a little carbon trace. So these contacts kind of are self-cleaning. As this presentation continues, it will become apparent why a short discussion on relays will bring a more clear understanding of programmable logic controllers. The programming language used to create programs for programmable logic controllers is based on the relay circuit symbols. The original control panels use relays for the logic, and the most common programming language today is relay ladder logic, and it evolved from the electrical prints and uses of the same symbols. As a matter of fact, if you look at an old electrical diagram for a relay control circuit, if you're a PLC programmer, you might at first glance think that it's an actual relay ladder logic program. Let's add our little relay diagram into an actual application, an actual circuit. We normally refer to that portion of the circuit which interacts with the operator as the public interface. You could say that there are three public interfaces to this circuit. The single pole, single throw switch, which the operator controls, and when he closes the switch, that energizes the relay. When he opens it, the relay de-energizes. Then you have a red indicator, and as you can see in the circuit, that the battery powers the red LED when the relay is de-energized. And then of course you have a green indicator which will illuminate when the relay is energized. This is the operator interface. So the operator has a switch to control the circuit, and then he has two indicators to indicate the state of the circuit. For power, we have an alternating current supply for the relay coil, but the relay contacts are actually controlling current from a DC source. Now, I show a battery made up of 4 cells. However, that DC source could be a DC power supply that takes the 115 volts AC alternating current, rectifies it into DC, filters it, and then regulates it at some specific DC voltage like 24 volts DC, 15 volts DC, 12 volts DC, 5 volts DC. It regulates it at some specific direct current level to control these other devices. And then of course the control circuit itself is a single pole double throw relay. Okay, looking at our circuit, when the switch is closed, the current flows through the coil, magnetic field pulls the armature down, opening the normally closed contact and closing the normally open. So you see now with the switch closed, the green light is on, but the switch did not turn on the green light. The switch that the operator can operate by hand turns the relay coil on and off. The contacts controlled by the relay coil then switch between the red indicator and the green indicator, supplying power from the DC source. So you could say that the contacts, the normally open, normally closed contacts, define the state of the relay. The normally closed contacts are true, or they conduct electricity, when the relay is de-energized. So the normally closed contacts are true if the coil is off. The normally open contacts are true and conduct if the coil is energized. So normally closed are true if the relay is off. The normally open are true if the relay is on. This is an illustration of an electrical circuit, not an actual conventional circuit diagram. You would not see documentation on a control circuit that was drawn in this fashion. We've laid this out so it's easy to see the relationship of the power sources, the switches, the coil, the contacts, and the loads. In this case, the loads are the two indicators, the red and green indicator. Before we change the look of this circuit into something more conventional from this kind of an illustration of a circuit, let's break the circuit up into a couple of pieces. First, you have the 115 volt AC section, which has three components: an alternating power supply, alternating source, a single pole, single throw switch, and a relay coil. Now realize that the relay physically is the coil and the contacts, but the coil of the relay is the only part of this 115 volt AC circuit. The other section is the 12 volt DC section, which includes the contacts from the relay. So the 12 volt DC, or just the DC section, because it could be 24 volts DC, has two LEDs, relay contacts, and the DC power supply. What I want you to remember is that there is an airspace between these two circuits. So if you follow the dashed red line, you will see that there's an airspace between anything electrical in the bottom half and the upper half. Now let's move on. Do you recognize this circuit? You should. You were just looking at it. What components do we have? We have a single pole, single throw switch, an alternating current supply, and a contact relay coil. Just the coil. What will happen when the switch is closed? When the switch is closed, the alternating current voltage source will alternate in one polarity, then the other 60 times a second. Whenever the switch is closed, it will power the relay. Now I show the relay going off as the current reverses, but remember that this is 60 cycles per second, which means that 120 times a second the voltage goes to zero and then keeps on going right over to the opposite polarity. So the relay doesn't have time to de-energize, even though I show it de-energizing in the diagram. Okay, do you recognize this circuit? This is the other part of the circuit that has a DC power supply, has two relay contacts with a common, one normally open, one normally closed, and we've gone so far as to identify the contact relay as contact relay 1, and then we identify the contacts as 1CR-1 and 1CR-2. Now remember that airspace in the previous diagram between the AC circuit and the DC circuit. You can really see the airspace here, but you can no longer see that these two relay contacts belong to that relay coil up there. Therefore we have to put nomenclature on them. We have to specify. So we wouldn't normally say contact relay 1, we would say 1CR, and then down below you have 1CR-1, 1CR-2. There's your red and green LED indicators. So when we close the switch, we get alternating current, and notice that the when it's de-energized up above, the DC power supply has a complete path for current flow through the red LED. When we've dropped the switch up above and energized the relay contact, we close the normally open contact, and we now have a complete path through 1CR-2 to the green LED. So you have seen now a simple illustrated type diagram for electrical circuit, and this is a more conventional style. Typically you divide up the AC from the DC, so all the AC is located on one sheet of the drawing set and the DC is located on other sheets, because the relay contacts very well will end up on a completely different sheet of the drawing set than the coil that controls them. You have to have very good nomenclature to identify what coil these contacts belong to. Looking once again at our illustrated diagram here, you see those two halves of the circuit. The upper half is the AC part, lower half is the DC part. Let's watch this circuit action one more time. And we watch this diagram, the animation of it, one more time. In the upper circuit, the AC circuit, you have a switch that energizes a contact relay. The contact relay, when it energizes, is going to open the normally closed contact that's represented by the parallel lines with a slash through it. That means normally closed. And you can see right now, because that contact is normally closed, the relay is in its normal state, de-energized. So the normally closed contact is completing the circuit for current to flow from the DC source through the red LED back to the DC source. However, when we power the contact relay, in other words, when we close the single pole, single throw switch up there and energize the contact relay, that is going to pull the armature down. It's going to open 1CR-1 and close 1CR-2. And then if we open the single pole, single throw switch, the spring is going to pull the moving contacts back up to the normally closed 1CR-1. Red LED goes back on. It opened 1CR-2 and the green LED is no longer illuminated. Returning to our illustration of a relay, doing a little review. Relay coil, pole piece, electromagnet. Pulls the armature down against a spring, opening the circuit between the common and the normally closed contact and closing the circuit between the common and the normally open contact. If we take our illustration and convert it to symbols, the circle on the right is the symbol for a contact relay coil, not the contacts, just the coil. And up above we have a normally closed and normally open contact with a common. So, and we call these form C contacts. So I'm going to flip this around so you can see it basically forms a C. So when you hear form C contacts, that means that you have a normally open, normally closed, and a common. You don't have two completely separate switches because both of them are attached to the common. Returning to our photo of a common relay, and by the way, relays come in much smaller formats than this and much larger. This is a circuit board mount relay, actually a fairly small one. Coil, symbol for the coil. Normally open contact, normally closed contact. Now at this point, because we are transitioning slowly into using the bits in a computer memory instead of the coils and contacts, I want to point out that these two contacts in a logical circuit are used to query the status of the coil. In other words, you have a circuit that when the circuit completes, it energizes this coil. That circuit could be made up of many individual devices wired in series, meaning it could be 3 switches from 3 completely different locations in the process. They're wired in series, so all 3 of them have to be closed before the circuit is complete and energizes the coil. So the coil then represents the state collectively of those 3 switches. So if in someplace else in the relay logic you want to query that coil to see if those 3 switches are all closed, then you would use the normally closed contact to ask the question, is the coil de-energized? If the normally closed contacts are closed, then yes, the coil is de-energized and it's true. Consequently, on the other side, the normally open contact, if you want to ask, is the coil energized, meaning that all 3 switches are closed, you use the normally open contact to query the coil, and if the contact is closed and you have continuity, then the coil is energized, and that represents collectively those three switches. So the normally closed contact basically is true if off, true if the relay is off, true if the relay is de-energized. The normally open contacts are true if the coil is energized, true if the coil is on or energized. Okay, this is a good point to take a break. So take a deep breath, hold it in, let it out. There is more. If you need to go get a cup of coffee, go use the facilities, get a soda pop, a beverage, say hello to someone, make a call, text somebody, check your email. Now's the time. Another look at our illustration of a contact relay. We have one Form C set of contacts. We have a common, normally open, normally closed. And remember that these contacts are used to examine the state of the coil to see if what is controlling the coil is on or off. And that could be one device or many devices in a separate circuit. And remember, the relay coil represents collectively the combined state of those devices. So you can use the normally closed contact to query the coil to see if it's de-energized, or you can use the normally open to see if the coil is energized. Well, let's take the situation where somewhere else in our relay control panel we need to query that coil. So we use a set of the contacts, and then a week later we need to query that same coil from a completely different piece of relay logic somewhere else on the panel. Well, we've already used up one of our contacts, and keep in mind that because they have a common, that electrically you can't use that common in two different places in your circuit. There's only one common terminal, and then there's a normally open, normally closed terminal. So we need more contacts. So we just drop in more contacts. They're all operated mechanically in synchronous, and we have a heavier switch, and we're going to need actually a heavier relay coil with more windings and more current, because remember that we have a heavier spring to pull back 4 Form C sets of contacts instead of 1. And we have to lift against gravity the 4 armatures. Actually, there's probably going to be 1 armature but 4 sets of contacts. So now we have more contacts on the same relay coil. So we have 4 normally opens and 4 normally closed. But remember, we only have 4 commons. So depending on how you're wiring up your circuit, you cannot use any more than probably 4 of these sets of contacts. You'll probably use either a normally open or normally closed from each set. Very pretty. Now this is a 4-pole double throw contact relay. I think you can see the coil there. We've drawn in a little phantom, and we point to the 2 screw terminals that you would hook into the coil circuit. And then we've got a moving contactor common, and if you look closely you can see that from the screw terminal you go a little to the left, down, and then back to the right to a black conductor that goes all the way over the other side, and then it rotates back and then into that copper blade you see there. And you can see the upper and lower stationary contacts, and you can see the screw terminals that they connect to, the normally closed and the normally open. So if you just take a second and look at this, you can see the similarity between this and everything we've shown you so far. In our illustrated relay, the moving contactor common was on the other side. In this case, they brought it back over to the same side for convenience of connecting it up. Now I said this was a 4-pole double throw. So you can see there are 4 sets of Form C contacts on here. So this would be the actual physical device that we were representing in the last slide that showed 4 sets of contacts. It's time to make a transition in our actual physical device. This is the original contact relay design. However, most popular industrial relays have a slightly different design. The difference between what you see on the left and the right, you see that there is no common contact on the right. Instead, you have a shorting bar that when you energize, it's pulled down, and when it's de-energized, it travels up. In the stationary contacts, there's 2 sets. What this gives you is 2 completely individual contacts for each position of the relay armature. That means that if there's an arc, the arc is divided between the 2 contacts. So that's an advantage. It reduces the possibility of the contacts welding together because of excessive current. So here's our new relay, our new contact relay, no longer with a common, which means that the normally open, which you see open right now, and the normally closed, which you see closed right now, could be used in 2 completely separate circuits because there's not just one common contact for both. So right now the normally closed is closed, so if you query this relay coil to see if it's energized, the normally closed contacts are closed, and they would have continuity indicating that the relay is de-energized. If you energize the relay, that pulls the armature down, opens the normally closed, and closes the normally open. And now you have a set of contacts that have continuity when the coil is energized. Remember, the only real big difference here is that we eliminated the common, and now we have separate connections for both the normally open and the normally closed contacts. This is the symbol for the coil. It's still a circle that says 1CR or has nomenclature in it. However, notice the difference in the contacts. Remember, before we had Form C contacts, so the contact symbols really needed to include that common connector, because they could not have been put in 2 completely separate circuits. The common has to be involved in both the normally open and the normally closed. With this newer design, the shorting bar design, the normally closed and normally open contacts are completely isolated electrically from each other. Once again, our relay coil, our symbol, if we need more than 1 set of contacts, one normally open, one normally closed, we simply add them in the stack. Of course, it's going to take a stronger spring and a more powerful electromagnet to move the additional mass and move the heavier spring. But notice now the symbols for our contacts. We have 8 separate symbols, not 4 sets of 2 symbols, but 8 separate. Okay, take a deep breath, hold it, let it out. There's more. So here's another opportunity to take a little break. This is a long lecture, and this is a lot of material to absorb in one sitting. Here we have just a tiny little piece of a much larger circuit, and in this 2 rungs of relay logic, and when I say relay logic, I mean real, magnetic relays. And you can see they call them rungs because it looks like a ladder with 2 steps on it. We have 2 relays. So the loads of these 2 rungs are 2 relays, 2CR and 1CR. 2CR, its function is when it's energized, it's okay to start the machine. 1CR, when it's energized, it's an indication that all 3 homing switches are at home. In other words, on this machine there's 3 axes of motion, and if they all are in the home position, then all 3 of those limit switches will be on, and 1CR will energize which will then energize, well, it'll close the contact 1CR-1. So looking at this diagram, the only connection really between these two rungs is that when the second rung goes true, in other words, 1CR energizes, it closes the contact in the upper rung that's part of the logic to say it's okay to start the machine. Now here's our three limit switches. Limit switches open and close by mechanical contact. Right now, and by the way, they're always drawn in the normal position and they're normally open. They are held open by a spring, and they have a little arm or a roller probe that sticks out, and when they make physical contact with something, it depresses the mechanical device and closes the switch. If the mechanical contact moves away, then the switch is pulled back open by the spring. So let's take and assume that all three of these switches have been closed because all three of the axes of motion, and they're probably hydraulic cylinders, they are all back in what's called the home or the home start position. Because remember, this is part of our okay to start logic, okay to start up the machine. So when all three limit switches are closed, that energizes 1CR, and that closes the normally open contact 1CR-1. We have another permissive or condition for okay to start, and that's the master control relay. A master control relay is a relay that is energized when all of the main safety systems have been met, such as light curtains and emergency stop switches. When they're all reset, then you press a button on the main panel to start the system. That closes, or I should say it energizes the master control relay, and this contact goes closed. Somewhere else in the circuit that you can't see right now, when the MCR was set, or reset if you want to put it that way, it probably started a hydraulic pump. And the hydraulic right now, the hydraulic pump is pumping up the pressure in the system because you don't want to start the machine until you're up to full hydraulic pressure. So at some point, that normally open switch is now going to close because that switch has an operator inside of the hydraulic system, and the pressure pushes it closed against spring tension. That spring tension is adjustable, very much like the regulator that we showed you in another lecture on basic electricity and magnetism. So the master control relay is reset, so it's safe to start. The hydraulic pressure is up. All of the axes are home. We're just waiting for the operator now to close the gate to show that there's no one in that location. When the gate switch, when the gate is closed, then this normally closed contact goes closed. So actually this switch was held open while the gate was open. Okay, at that point 2CR energizes, saying it's okay to start. Now you don't see any contacts marked 2CR in this diagram. That's because they're in many other locations in the electrical schematic, and they are now permissives or conditions in other rungs of circuit logic to say that it's okay to start. Let's take another look at a real relay diagram. If you've never seen one of these before, you're probably seeing too much information right now. So we're going to simplify this diagram. The first thing we're going to do is we're going to take the power source. Up at the top there, you see it says L2, L3, goes through a couple fuses to a transformer that supplies power to this relay ladder electrical diagram. So we're going to take that electrical source and we're going to simplify it. It's a fused 120 volt AC source. We're going to simplify it into a line cord that goes over and plugs into the wall, because it would do the exact same job. And after all, there are fuses in the fuse box in your home that would replace the fuses shown in the diagram. So we've simplified this to show an electrical circuit, and if you scan down through it, you'll see that there are electrical conductors that go from left to right through fuses, switches, and lights. Switches and lights, relay coils, etc. So what you're looking at right now is actually 3 separate circuits that all share this power source. The first one is very simple. You've got a fuse there, that's just in case there's a short, and then you have a switch that says system lights, and then it shows a light, LT101. Literally, that is the light inside of the control panel, so you can turn it on to do maintenance in there. The second diagram is a starter circuit for a motor for an oven recirculation fan. And you can see the nomenclature over on the right hand side. It says motor starter oven recirculation fan. Now a motor starter is nothing more than a large contact relay with additional devices called motor overloads. And if you look just to the right of the circle for the coil, you'll see a normally closed contact that says OL under it. That's the overload. So if too much current is drawn through this line, the overload pops open. That's why they call them motor starters. So the only difference between a starter and a contactor is a starter has the overload elements. So if you look at this rung, you've got a selector switch, going from left to right now. You've got a selector switch, and it goes over and it energizes the motor starter. So that's one circuit. And then here's another identical circuit, only it's a motor starter for an oven exhaust fan. But you see how these form steps in a ladder. So this is a classic relay ladder diagram. This is an electrical circuit. This is not a PLC program. But later on you're going to see how PLC programs look a lot like this. Now we're going to make this a little more interesting. What you are looking at is a pneumatic cylinder. And pneumatic means air. So the cylinder is operated. Right now it's in the retract position. It's operated by air pressure through something called a solenoid valve. A solenoid valve has 2 electromagnetic coils that are used to pull the inward workings of the valve, called a spool, back and forth to control airflow to one side of the cylinder or the other. And inside of this cylinder is a piston, and at each end of the cylinder is a port. If you put compressed air in the front, it pushes the piston to the rear. If you put compressed air in the back, it pushes it to the front. What's of interest for us as controls people are the 2 sensors. And you can see that one of them has 2 LEDs lit up, power LED and status LED. The power LED just means that there's power there to power up the sensor. The status LED says that that sensor right now is sensing something. Notice that the other sensor, its status LED, is not illuminated. And that's because the sensor that's not illuminated is the cylinder extended sensor. Right now the cylinder is retracted, so the status LED at the back of the cylinder is now true. Now remember in an earlier lecture on basic electricity that if we took a magnetic field and we brought ferromagnetic material into close proximity, that it would disturb the magnetic field and we would thereby sense the presence of something. So right now that sensor is sensing the presence of the piston in the full retracted position. Now those sensors slide in those grooves that you see them mounted in. So they're adjusted to a right position to sense the presence of the piston. Now these sensors aren't necessarily magnetic proxies. They could be inductive proxies or something called Hall sensors. Now we're not going to go off discussing the difference of these sensors, but just keep in mind these sensors have a field that is disturbed when the presence of a particular element shows up in close proximity. A closer look, you can see that the status LED below is dark and the status LED above the retract position is illuminated. Okay, now if we apply compressed air to the back side of the piston, that pushes it forward. Now look at the status LEDs. The one in the back of the cylinder is now dark and the one in the front is lit up. So these two status LEDs are part of two cylinder sensors. These sensors act like switches that are used in a circuit, and when the switch closes, it's saying, in this case, that the cylinder is in one position or the other. Now, of course, if you put compressed air on the other end of the cylinder, it retracts back, and you see our status LEDs are back to the original state. This is a pneumatic valve. This is a solenoid valve, and on each end of it you see electrical connectors. So inside the black plastic, we'll call them boxes that have the little knobs on the end, are coils of conductor, and then in between the two black boxes, going through the entire body of that valve body there, is a spool. It's basically a rod that has grooves in it, and as the two solenoids pull the rod back and forth, it connects chambers between the ports. You can see two of the ports on the top of this valve where you thread in the fittings. So you have two solenoids that can pull the spool in opposite directions, and this makes up an air valve. So these two solenoids, remember, a solenoid is a coil, like a relay coil. So when you look at electrical diagram, we have a slightly different symbol for a solenoid than we do for a coil, so you can recognize the difference, and you'll see in a minute. Okay, here we have a circuit, and we have three rungs of, we'll call it relay ladder diagram. This is an actual electrical circuit, not a PLC program, but they look a lot alike. In the first rung we have a normally open push button, and for a load we have 1 CR, a relay coil. In the second rung we have a relay contact, normally open contact, and for a load, in other words, if that contact closes, it's going to energize this solenoid over there, 1 SOL, and its nomenclature says that it's extend. And then in the third rung, the normally closed contact from 1 CR, if it's conducting, will energize 2 solenoid and will retract the cylinder. Of course, we recognize that inside the dashed blue line, that is one device. 1 CR coil and 1 CR-1-2 relay contacts are all one device. So when you push the push button, 1 PB, you are affecting the other two rungs in the circuit. So when it's de-energized, this contact will be open and 1 SOL will be off. When it's de-energized, this will be closed because it's normally open, and 2 SL will be energized. Looking at this right now in the normal state, you're not pushing the push button. Is anything in this circuit currently energized? Look at it very carefully. You have live voltage on the two vertical lines. So over on the far left, that vertical line is the hot of power, and the one over on the left, the vertical line, is neutral. If this were a 120 volt circuit, if it was 24 volts DC, you probably have plus voltage over on the vertical line on the left and negative on the vertical line on the right. So following the path for current flow, do you see a complete path? Of course you do, because 1 CR is de-energized, 1 CR-2 is closed because it's normally closed, and it gives a complete path of conduction from the power rung on the left to the power rung on the right, passing through 2 SOL. So that solenoid is energized right now, and it has shifted the spool in the valve to allow air, compressed air, to go to the front of the cylinder and push the piston all the way to the back so it's in the retracted position. Are any of the contacts currently true? No push button push, just the way you see it. Are any of the contacts currently true? Remember, you got true if on, true if off. 1CR-2 is true because it's off. In other words, it will have continuity. It's true because it's off. Are there any that are false? Look real closely. Push button 1 and 1CR-1. They're both normally open, and right now they're open. No one's pushing the button. The relay is de-energized, so 1CR-1, normally open, is open. So it's false. With one push button closed. Okay, pretend like right now somebody's pushing that push button. That's going to allow current to flow through and energize 1CR. In that state, with that scenario, is anything energized? I just gave you one. Yes, 1CR is energized. That closes the normally open contact 1CR-1, which allows current to flow through 1 SOL, energizing that coil, which is a solenoid. It shifts the spool to the other side and allows compressed air to be pushed in the back of the cylinder, pushing the rod out and extending it. Looking in the state that it's in right now with the button pushed, are any contacts true? 1 PB and 1CR-1. They're true because they're on. Are any of them false? I think you're catching on here. 1CR-2. Let's look a little more extensively at this circuit. Now, this is a very, very simple circuit, but it embodies most of the typical logic for a relay electrical diagram. You have switches that are operated from an external source, like a human being pushing the push button. You have relay coils that move the movable contacts between normally open and normally closed, and then you have circuits controlled by these relay contacts. Now, when it comes to electrical diagram or to standard relay ladder logic like you would have in a PLC program, there's a line that divides two sections of these rungs. This line right here divides the actions from the permissives, or you could say the actions from the conditions and permissives that need to be met to cause the action. So on this side we have actions. We have solenoids and we have a relay coil. The solenoids are actions external to the control. The coil 1CR is internal to the coil, to the control. And then on this side we have conditions or permissives. Now, actions are on or off. Conditions or permissives are always true and false. The first one is it's a push button, so it's true if pushed. The second one is true if on for the relay coil, and the third one is true if off for the relay coil. So conditions and permissives are always true or false. Don't say on and off. Now you can say 1CR-1 normally open is, you can't say it's on if 1CR is energized. You can only say it's closed. Allows continuity. It's never on. None of these conditions or permissives are ever on or off. They're true or false. The actions, on the other hand, are on or off. So we have a push button and we have two relay contacts. But these are all conditions or permissives that will cause actions when they're true. So these are our external interfaces from the control system to the real world. The push button is the external interface to the operator, And the two solenoids are the external interface out to the public, to cylinders that extend and retract. And then we have internal interfaces, the two relay contacts and the relay coil itself. And of course, that relay is an actual device. We're making progress, folks. Any minute now we're going to be moving into new territory. Actually, this is new territory. You are looking at the most common electrical industrial rung ever, and it's called a start-stop circuit. You see two push buttons, a normally closed, a normally open, and then you see a relay coil. Bypassing the normally open push button is a relay contact. This is the standard start-stop circuit. For the start button, we have a normally open push button. For the stop button, we have a normally closed push button. And just jumping out for a minute, here is the top is a normally closed contact and the bottom is a normally open. So this could be a relay contact or it could be a push button. In this case, we're going to say it's for the two push buttons, because remember, for a start button you have a normally open, which would be the one on the bottom, and for a stop button you have a normally closed, which is the one on the top. So if you look at the two sets of contacts, they are 100% identical. The difference is how they are connected. So normally when you buy a industrial push button, all you get is the operator, which is just the spring-loaded button that goes in and out, no contacts. Separately, you buy a contact block. And the contact block that you're looking at here, you're looking at two of them. It is the most common contact block. It has one normally open, one normally closed. The top contact is normally closed, the bottom one is normally open. I show the block here twice to show you in the upper one how you would connect up a normally closed contact. So the push button is the push button, but the contacts that are operated can be wired up as a normally closed or normally open. Actually, you could use both contacts, but you wouldn't use this both in the same circuit. So the upper one is wired up like the stop push button, normally closed, and the bottom one is wired up like the start push button, normally open. Okay. We also have a contact relay, and the relay contact in parallel with the normally open push button, I show a dashed line. In electrical diagrams, we did this quite often to show that there was a mechanical link between the contact relay and the relay contact. We don't do this anymore. I threw it in here just to emphasize that that contact is controlled by that relay coil. So if you energize that relay, that contact is going to close. If you de-energize the relay, that contact is going to open. So look at that circuit. Right now the normally closed push button is closed, the normally open is open, the relay contact is open, and the relay is off, de-energized. However, if I push that normally open push button, the start button, that closes the circuit from the left power rail, vertical line, all the way over through the relay coil to the right power rail, vertical line. The relay coil energizes and forces the contacts to change state. So the normally open contact in parallel with the start button now goes closed. So now you have two paths to the relay coil, through the normally closed push button, through the normally open push button that you're holding closed to the relay coil, or the current can flow around through the relay contact, which is now held closed by the relay coil, to keep the relay coil energized. So if you let go of the normally open push button, you still have the path for continuity through the relay contact to hold the relay closed. So we call this seal-in logic. That's called a seal-in contact. So you energize the relay, and the relay holds itself on through that contact. Well, how would you get this to shut off? If the normally open push button is now open because you let go, but current is flowing through that relay contact over to the relay, how would you break this circuit or open it? Yes, you push the stop button, the normally closed button. When you push that, now there's no continuity anywhere through that circuit. The relay coil de-energizes, the relay contact opens, and when you let go of the stop button, it goes closed. The normally open push button is still open, and the relay contact is still open. This is your classic start-stop circuit, used to control millions of motors out there in the industry. Okay, there's your stop button and there's your start button. The red and green buttons, that's the operator. And directly behind it, you see some plastic and some screw terminals. And both of them have the identical screw terminals. That's because they are those contact blocks I just showed you. And then, of course, you have a relay. Now, I'll just throw in another point here. I showed this earlier, but I'll show it again. This design provides better protection against contact welding than a single break design. This feature also provides separation of the normally open and normally closed circuits. Double break contacts open the circuit in two places, creating two air gaps, reducing the possibility of welded contacts compared to this single break design. Now, I'm very familiar with these relays, and I realize you might not be. However, I can tell by looking at the numbers on the screw terminals which two terminals you would wire up in parallel with the normally open push button for a normally open contact to bypass the normally open push button to seal in the coil. Now I have them marked there. Okay, everybody take a deep breath. Let it out. The next transition is really big. We're going to make a huge quantum jump here in the next section, but this is also a good time for you to take a breather, grab something to drink, pause if you're watching this, in a video. Otherwise, take a quick break here, and then we'll get right back.